Hello again. This is starting with problem 4 for the last drill session here. This is a super hard problem. I had to use Wikipedia for this. Wikipedia, that's just fun to write. I had to use Wikipedia to look it up. Turns out it involves the Gilman reagent. So really quickly, let me pull up the Wikipedia page for it. Yeah. Okay. This is the this is the Wikipedia page that I used to understand it, and this part here is the most important part. It turns out when a Gilman reagent, which is this thing right here, is reacted with a alkyl halide, which is this thing right here, stuff just rearranges in this transition state. And I tried to look at the mechanism for that transition state, and one of the websites said that it's not fully understood how that happens. So I stopped there, but I'll show you how it is relevant to that problem. So real quick, let me see if I can. No, I can't do that. Hold on, let me see if I can put that. Yeah, that's the link to it if you wanna look that page up yourself. But let me try to make it relevant to this problem. So essentially, in the first steps here in A and B, you're forming a Gilman reagent, and the Gilman reagent that you're gonna form is this guy right here. Oh, yeah. Sorry, I need to erase this. I think that's the Gilman reagent that you're going to form, and so this is this is ionically bound, so they dissociate. And you add this to this alkyl halide that he showed. It's 1, 2, 3, 4, 5. And it is a complicated intermediate. You can use that Wikipedia page that I showed, kind of plug it in, and see if you can kind of figure out how the molecule rearranges. But it ends up adding one of these R groups right here, that R group, to this R group, this alkyl group, that alkyl group, to this alkyl group, and it forms the product C is this product right here. So let me see if I can emphasize the colors here. So it looks like this. That R group right there is this R group. And then this R group right here is this R group, and that's the bond formed between them. So let me make sure I got that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay, that's the structure that he drew. And then, so those end up together. The Li and the lithium and the halide end up together. And then copper ends up retaining one of its R groups. And I'll just kind of put this. Like I said, that all happens in this complicated intermediate. And I would go into that mechanism, but I just don't know. I just don't know how relevant it is, and the fact that I'm not sure it's 100% fully understood. I think it's kind of beyond the scope of our class. But the point of a Gilman reagent is that you have this nucleophile right here that's going to attack this alkyl bromide, and you're doing a nucleophilic substitution there, and it does some fancy rearranging, and this is standard stuff. The lithium is going to end up with the halide. The alkyl group attached to the halide is going to add with one of the R groups on the copper ion, and then the copper is going to retain one of its R groups, and they all end up neutral. So that's number 4. That was hard. Number 5. Let me move some of my papers around really quick. I think number 5, I'm pretty sure the point of this question is to make you understand that a Grignard reagent is used for things like esters and things like ketones, those carbonyl groups that we've been talking about. But because essentially what forms is your nucleophile, your alkyl nucleophile. So in this one, it'd be 1, 2, 3, 1. Let me erase some of this. Essentially, the point of a Grignard reagent is so that you can add a carbon group to a molecule through that nucleophilic addition. Because you're winding up with extra electrons on there and a negative charge, if you react this with an acid, like this carboxylic acid, 1, 2, 3, 4, 1, 2, 3, 4. You are going to do an acid-base reaction, and so you end up just forming these guys. Like this is going to lose its proton right here. That proton's leaving. You end up with a negative charge on that oxalate, and that attracts the positive charge from the Grignard reagent. So these two get together, and then the hydrogen ends up with this alkyl group that in a normal situation would do a nucleophilic addition, but because this carboxylic acid is a pretty good acid and it's willing to donate that proton easily, you just end up with the acid base reaction. So that should be number 5, and then we keep going. Number 6. I'll read the question and then I'll scroll down to get some room. Which of the following synthesis plans is reasonable if you want to make the compound below? So the way I'm going to approach this problem is I'm just going to make the compound below, and then the answer choice that fits with the way I made it is the right one. That way I don't have to make all of these and see where each of their faults are. So all of them start with benzene. I'll start with benzene. Okay, if I want to create this group, I see that they are, like, these two groups are meta to each other on the benzene ring. If I added bromine first, it's a ortho-para-director, so it wouldn't direct direct meta. But this, just because I recognize that that's an alcohol and it could have started off an acyl group, and it would meta-direct, I'm going to start with it. So the acyl group that I would start with there is, I've got 1, 2, 3, 4. So I would start with a an acyl chloride that has 4 carbons attached. So 1, 2, 3, 4. And that's a butanoyl chloride right there. And I would add that sucker to the ring, Friedel-Crafts acylation style. And it would give me this. Then is a pretty good time to add that bromide group. So I would add it, just a bromination of that benzene ring. Br2 and FeBr3 is going to give me this. And then at that point, if I want to, I can use the, so at that point I can use a Gilman reagent to add that chlorine group right, or that methyl group right there. So I'm just going to simplify that as Gilman. And I know that it would give me that product. So looking here, I've got benzene. That's all of those are benzene. Then my next step is the butanoyl chloride, and so that knocks out D, E, and B. And then my next step is Br2, and so that knocks out A. Let me just verify that C is the right one. And after the bromination, I do a Gilman. That's this sucker right there with an aqueous workup, and that gives me the product. So the right answer to this one is C. And I think I will continue in another video.